Last week we did a lab where we looked at a collision in one dimension between two objects. We analyzed the momentum before the collision and the momentum after the collision, and we found in some cases that momentum was conserved, and then in some cases we found that momentum was not conserved. A lot of cases momentum was lost due to external factors like friction and due to an uneven floor and so on. But in the end, we saw what the relationship ended up being experimentally between a collision, for a collision between two objects in one dimension. Today what we're going to do is do kind of the same thing, but in two dimensions, and we're going to do it in a different way. Here's how the general experiment is going to be set up, and I'll give you details of how to collect data in a few minutes. You're going to have two objects, two pucks, two orange pucks. You're going to take those orange pucks and set them wherever on the floor. Object number one, object number two. You're going to fire those pucks with your hands towards each other. Now, you don't want to fire them directly at each other because then that's not going to be a two-dimensional collision. They're going to bounce off of each other and it'll be a one-dimensional collision. So fire them at each other at an angle. It can be at 90 degrees to each other. That's okay. It can be at a glancing collision like this. It doesn't really matter as long as they hit each other and bounce off of each other at angles. Got it? So 90 degrees, a glancing collision like this, anything except straight on. Now, if you do it like this, you might look at this and say, oh, there's lots of funny angles there. I don't want to do it that way because that's going to make it more difficult. That's okay. Don't sweat it. It's not going to make it any more difficult if you do it like this than if you do a 90-degree collision. With the way that we're collecting data, it ends up being the same amount of work. So don't lose any sleep over that. All right. That's the basic setup. You know, of course, that we're going to have to collect the mass of both objects, given that you want to identify whether momentum is conserved here or not. So measure the mass of both objects. I'll give you a little shortcut, though. Both objects that you use are going to be the same. They're going to be these little orange hockey pucks here. The mass is going to be the same. So if you measure the mass of one of them, it's pretty safe to assume the mass of the other one is the same. How are we going to collect velocity data, though? Okay, this is where it differs dramatically from what you did in the last activity. As opposed to using the AirLink and the SparkView app that you used last time, you're going to use your iPhone again, but this time your iPhone is going to directly collect the data by videoing this. You're going to hold your iPhone somewhere above the collision point. Ideally, it's directly above so that we don't have what's called parallax error. You guys know when you're sitting in the passenger seat of a car and you look at the driver's seat, and you look over at the speedometer, it sometimes looks like a speed is a certain value, but it's not actually that value. When you look at it from an angle, it's different than it really is. Okay, only the driver can see the actual speed because he or she is the only one looking straight at it. We call that parallax error. If the camera is not directly above this, then we get parallax error. So we want to make the camera as much as possible directly above this. But on the other hand, we also need to keep the camera steady. In order to keep the camera steady, the easiest way is to probably have it braced against a desk or braced against a lab bench if you're working in a biology lab, or braced against something that makes it a little bit easier to keep it steady than just holding it in your hands like this. If we hold it in our hands and there's a little bit of shaking, then the software that we're going to use to analyze this doesn't know whether the motion is from the pucks moving or whether it's from your hands moving. Does that make sense? So keep it as much as possible directly above, but also you want to keep it steady. Once we collect the data on our video, you're going to email it to one person in your group. Doesn't have to be to everybody this time. Okay, to one person in your group. And then that one person is going to log onto a computer with everybody else in your group, and you're going to analyze the data using a software program that I'll provide for you. All right? Couple little things, okay, before I show you how the software program works. Number one, we already said that you want to have the camera as close to above this as you can. Number two, we've already said that you want to keep the camera as still as possible. Number three, we need to put in this field of view a meter stick. And the reason we want to put a meter stick in there is because we need to tell the software program what a certain distance is. The computer doesn't know what a meter is, so we need to tell it what a meter is. That make sense? If you happen to cut off a little bit of the meter stick in your video, that's okay. It doesn't have to be a meter that's our defined distance. It can be a half a meter that's our defined distance. We just need to change a little setting, that's all, in the software program when we get there. So, collect your video, email it to yourself. Once you've emailed it to yourself, we want you to save it to the desktop of your computer. Got it? Save it to the desktop of the computer so we know where to find it. Then you're going to have a software program called Tracker that when you open up is going to look something like this. Here's how it's going to work. When you open a software program, you're going to click the top left-hand corner here, which is going to allow you to open the video that you want to analyze. That's going to be located, should be on your desktop, so it's easy to find there. Okay, as it imports it, you're going to see a picture on your screen here, which is going to have your video. Then you go on to set a frame of reference. Okay, and the instructions, again, are in that booklet that I'm going to hand out to you. You want to set a frame of reference. The frame of reference basically says to the computer, let's measure the distance from here. Right? We need to know where it's measured from. We can't just say the position is 4 meters. It's 4 meters from what? It's 4 meters from our frame of reference. Okay? So set your frame of reference, and again, the instructions are on the sheet for that. Then you want to set your calibration tool, which is the whole point of having that meter stick in there. Okay, wherever we have our meter stick, which you can see in my video, it's right there, we want to set that calibration tool for a meter or for a half a meter or for 20 centimeters, whatever happens to be convenient for what you can see in your video. Set it for whatever distance so that the computer knows what a defined distance is. So you've got your frame of reference. That's the crosshairs that you see right there in purple. You've got your meter stick and your calibration tool that you can see circled in blue there. Then you're ready to actually collect some data. We have 2 objects here, right? Normally what we do is create in the software program 2 point masses because we have 2 objects. 1 point mass for each object. What I'm suggesting you do here is create 4. Why 4? No, because it's easier if we separate initial and final rather than, say, have data for object 1, initial and final together. Because then I have to separate it later on in a spreadsheet. It's easier if I say object A, right, create my point masses. Object A is object 1 initial. Object B is object 2 initial. Object C is object 1 final, and object D is object 2 final. Make sense? Then we've got data separated for initial and final, as opposed to data together for initial and final, where we have to separate it later on manually. So create 4 objects. Even though in the instructions it doesn't tell you how many objects to create, okay? Create 4 of them, even though we only have 2 objects. And then you're going to follow the instructions for actually clicking on the data, clicking on the puck, and creating your position time data. Now, a couple little words here about setting up the experiment so that at this point you get enough data. Make sure that when you're pushing these pucks, make sure that, number 1, you have enough data before the collision, but after the pucks left your hand. So in other words, what you don't want to do is push the pucks and be pushing them almost to the point where they collide, because then you don't have any data after you released it before they collided. Does that make sense? So push it over a distance, right? Push it and then let them slide for a bit of a distance before they collide, and then let them slide for a little bit of a distance after they collide, but before they hit the meter stick or before they leave your field of view of your camera. Right? You want enough data both before and after the collision where there's no external forces acting. The other thing is, when you're analyzing this collision, make sure that you're analyzing just before and just after. Okay? If we go back to our original picture here, we don't need to analyze all of this stuff. We need to analyze this. This would be object A, initial. This would be object C, right? Object 1, initial and final. Object B or object 2, initial. Object D or object 2, final. You want to analyze this section in here, just before and just after the collision, right? So once we have our data here, once we've done our thing with the software program, you're going to see in the bottom right-hand corner an option to select a table for mass A, B, C, and D. Remember what those are, right? A and C are object 1, initial and final. B and D are object 2, initial and final. You're going to select one table at a time. Highlight all the data by clicking Control A, and the instructions are here for that. Copy it by going Control C, and then within Google Classroom, create a spreadsheet and paste that data in there. Do the same thing for object B, for object C, which is again the first object but final, and object D, which is again the second object but the final data for it. Once you have that, you're going to create 8 graphs. What are the 8 graphs? They're all position versus time. We're going to have position versus time, x component of object 1. We're going to have position versus time, x component of object 2, initial. We're going to have position versus time, x component of object 1, final. Position versus time, x component, object 2, final. And then you're going to do the same thing for the y components. Do it in the order that it's listed in these tables. You've got this template, by the way, already created for you in your Google Classroom. So you can see everything that you see up on the board right now, you'll see in your document that I've already created for you in Google Classroom. Copy and paste your graphs once you've got them plotted into here in the order that it's listed right here. This should be the y component, by the way. Copy and paste them in that order right there. Just delete that purple stuff. Get the slope of each of those graphs, type them in right here. And then once you've got that, calculate the initial momentum for the x component. Calculate the final momentum for the x component. And then do the percent difference. What's percent difference? Well, the general formula for percent difference is actual minus theoretical value over theoretical. And usually we take the absolute value of that so that it's a positive number times 100. The actual value would be the final amount. The theoretical value would be the initial momentum. Because the initial is what it should end up being, what it theoretically should end up being. The actual value is what it actually does end up being, the final amount. Do the same thing for the y component. And then write a conclusion. Was momentum conserved for the x component? Was it conserved for the y component? How do we know? And then, of course, you delete whatever's in purple, create some sources of error. Make sense? So the bad news is there's 8 graphs to plot here, although they are relatively straightforward graphs, just position versus time, find the slope, which Google Sheets will do for you. If you have trouble with plotting the graphs, I can help you with that. The good news is this isn't due till next Monday, so you've got 6 days to do it. And because there's 8 graphs to plot and a lot of work that you're going to end up doing together, I'm going to accept one per group, one hand in per group. Okay, that means somebody in Google Classroom, you've all got this created in your Google Classroom, but you're not all going to submit it. What's going to happen is, let's say James is kind of the leader of his group. He ends up submitting it, but you're all going to end up working on his assignment. You can do that on the same computer, or you can simply share it so that everybody can do that. You got to make sure, though, when you do this, hey, James is going to be the one that submits it. I'm going to see that he submitted it. I'm going to give him a mark for it. You got to make sure that everybody else in the group has their name clearly typed into the actual lab write-up so that I can give you all marks for it. That make sense?